Good morning. We're going to focus on flood control benefits of green infrastructure within the urban drainage system. My company, Watearth, is a water resources and green infrastructure firm. We also work on hydrology and hydraulics projects and water quality. I will go through a number of detailed tables. For those of you who'd like a copy of those, you're welcome to email me at jwalker@watearth.com. Now, some of you may have come here today expecting to hear about green woofs and watersheds. Hopefully you won't be too disappointed. We're going to focus on bioretention and permeable pavement instead. I've gone back through some of our previous modeling projects and pulled together data on performance. Now, many of these projects were not focused on flood control. However, I have included the largest design storm event that we modeled for each project. So I've got it broken down into redevelopment, new development, and watershed level. And while it's hard to draw a hard and fast conclusion, in addition to rainfall depth and soils types, the primary driving forces in performance appear to be impervious cover of the project, the portion of the project or drainage area dedicated to green infrastructure, and then also the geometric configuration, both horizontally and vertically of the green infrastructure. So on most of these projects, we do have a pretty good peak flow reduction. You can see the rainfall depths range from about 3 inches up to about 8 inches on these redevelopment projects. And I'll go through just a few examples of them. The first one is Nuview Elementary School, located in Riverside County in Southern California. The goal of this project was 100% stormwater infiltration. The soils were there to support it. I'll jump back to the previous table, and you'll notice that many of these rows are highlighted in blue. Those are all projects that had primarily clay soils. And most of the projects that I'm going to present today had primarily clay soils. Some we had the help of the well-draining soils, the Nuview project being one of them. So hydraulic conductivity of about 1.2 inches per hour. It was a parking lot redevelopment that also solved structural flooding of an existing building. The primary green infrastructure tools were porous pavement, being porous asphalt, and also infiltration basins and trenches. With overflow elements built in for redundancy and resiliency to provide overflow into other features as well as play fields, so that overall, even if maintenance issues led to decreased performance, we'd still achieve the project goals over the long term. Here's some finished photos from our design. The driving lanes and parking stalls within the center of the parking lot are porous. You can also see some solar arrays that were installed as part of the same project. And I'm in there to give you a feel for scale. And you'll notice the rocks were really big, and that's so the kids don't pick them up and throw them. The next project is in San Francisco, and it's a 42-acre redevelopment. The soils varied, but primarily well-draining with an average saturated hydraulic conductivity of 0.43 inches per hour. And the goal on this project was to meet criteria for the combined sewer system, being a 25% reduction in the 2-year runoff volume. So it's still in feasibility. We haven't modeled larger events at this point, but very easily achieved that requirement. But you will see green roofs could be an option, but they would require 44% of the site to have a green roof based on our assumptions, whereas bioretention and permeable pavement are much lower percents. The final redevelopment example is in Los Angeles at the LAC+USC Medical Center. This is an 84-acre redevelopment, and the work was done as part of the master plan EIR report. So very poorly draining soils here, 0.085 inches per hour. And we looked at permeable pavement, bioretention, and stormwater wetlands, which were recommended by the master plan consultant, as shown on this graphic. And we found for the 8-inch 100-year 24-hour event that we had very good performance as laid out to reduce the proposed peak flows below existing conditions. Now, they didn't get down to undeveloped conditions. That was not a project goal, but we are improving conditions compared to the existing site, which essentially had no stormwater controls. And then we also looked at historical records of data for about 40 years in a continuous simulation model and showed in general most of the maximum annual peak flows are at or below existing conditions. Moving into new development projects, the first project is compared to proposed conditions without LID, and the second two are compared to existing conditions. So when we're comparing to existing conditions, we're really just trying to match that peak flow. I mean, we're a little bit lower in some cases. The second project driven primarily by water quality performance. The first project is located in Sacramento, and we'll get into that in a bit here. But the goal of that project was not really reducing the 100-year peak flow. Centralized flood control basin was planned, so the reduction helped, but the primary goal was really storm drain reduction in the smaller events. This first project located in the Gulf Coast, roadway runs through the center of an industrial park. There's also significant floodplain management issues where we're realigning the creek, including stream mitigation and providing regional detention. So the LID, or green infrastructure, was a very small portion of this project, but the roadway itself is being mitigated by low impact development within the right-of-way. It's a major thoroughfare. There's actually plenty of right-of-way. There's about 31 feet available within the median for green infrastructure features. And you can see that we've met from the lower hydrograph. The proposed peak flow is just right at existing conditions. Now there's a double peak, and that's because for this portion of the system, there's an initial release from the vegetated swell and then a later release from bioretention. Now if you visually look at that graph, you might say, well, there's more surface area under the curve or more runoff volume. And that is the case. The criteria for this project was peak flow based rather than to specifically deal with excess urban runoff volume. So the overall big picture project is looking at things like downstream impacts to peak flows. So we can see our hydrographs from the vegetated swells. They fill up nicely for the 3 design storm events and drain out relatively quickly. For bioretention, a much longer holding time. We see by about hour 66 or 72 in the 100-year design storm event, it's drained out pretty completely. And these are large facilities. This project wanted to use the LID for flood control. So these aren't little 12-inch rain gardens. These are, 4.5, I think 4.33 feet deep. The vegetated swell, because of the slope on it and the emphasis on conveyance, doesn't fill as completely as the bioretention, which is located in the flatter area near the outfall. The next project's located coastally in Los Angeles, a very small 7,000 square foot site with significant design issues, liquefaction, high groundwater levels, small site, and so forth. So a lot of alternatives were discarded, but the best alternative that we've found is the use of either planter boxes or lined bioretention, which both function very similarly. So this project included modeling of the site, but also detailed hydrology and water quality modeling of the outfall system, the Grand Canal. It's in an environmentally sensitive area, which is part of the emphasis. So we can look at the hydrographs from the lined bioretention, which we might call biofiltration, because there's really no infiltration into the ground. It's all accomplished by storage and some evaporation, as well as filtration for the water cleaning benefits. So the drain rock layer in this case actually has the higher hydrographs. It's about 30 inches deep. The growing media is 36 inches deep to specifically target pollutants. And then the surface storage is about 18 inches deep. And that does fill completely with the recommended alternative. Hydrographs in the upper left-hand corner from the 100-year event were essentially right at or a little bit below the existing peak flow. These discharges are tiny, but it is a small site. And then in the Grand Canal, the receiving system, we really would not expect a hydrologic impact after the LID features, but that's been checked and it's right at existing conditions. We can also look at the continuous simulation modeling in the upper left-hand corner, the maximum annual peak flows from the site, less than or equal to existing conditions. The upper right-hand corner, no change in the Grand Canal. And then the lower graph is from the site, and it looks at exceedance frequency curves from the site. So our peak discharges are less than existing conditions for the range of events modeled. Usually for hydromodification management, we're looking at, say, less than a 2-year to somewhere up to maybe a 10-year event. And what about water quality? So the water quality performance of the biofiltration is really excellent. We did note in the 2-year event some very slight increases in TSS, or total suspended solids, and also COD, or chemical oxygen demand. The 2-year event's bigger than a water quality event. We just looked at it as a moderately representative design storm event. The annual data is much more telling. So we've recommended a pre-treatment with a vegetated filter strip to help cover those items. Finally, we have a 233-acre mixed-use project in Sacramento. Not so focused on flood control for the LID, but we did see reduction in storm drain sizing. Some of these features were very small, like 6 inches of storage depth, some a bit larger. But we saw a really promising 53% reduction in annual runoff volume from the features, mostly accomplished by an increase in evaporation due to the clay soils. And what about watershed benefits? We are seeing those as well. We've got a couple different projects in here. For those of you who'd like to learn more about one in the Bay Area as part of a green infrastructure master plan, we have a very brief video on YouTube on that. This project's located in Fort Worth in an urbanized watershed with fairly significant flooding issues in less than a 10-year event. So as part of a land plan study, areas for green infrastructure were identified. We've put those into an EPA SWIM model and shown varying degrees in reduction in the 100-year event, which is 9 inches, depending on the extent of the LID. So ranging from a few percent up to very high. And that brings us to operations and maintenance being very important to ensure the long-term performance. The Envision certification process includes points for O&M, so very important thing to incorporate. Public education and outreach is also very helpful. Santa Monica is excellent at taking care of that. Riverside County Flood Control District, we worked with them on a really fabulous demonstration project, incorporating interpretive signage throughout. These particular signs won a National Communications Award, and the project itself has been very award-winning for the district. I can also take a funner spin, like projects with the city of Citrus Heights in Sacramento area, and use interpretive signs as an example and a way to highlight maintenance activities that need to be done for the long term. A few final thoughts. Green infrastructure can play an important role in providing resiliency and redundancy in our infrastructure systems. There are possibilities to meet multiple goals with green infrastructure. It's important to know what those goals are. It can very readily be integrated with flood control and may require certain design modifications to customize to that. So again, if you're interested in any of the detailed tables, feel free to email me at jwalker@watearth.com. Thank you so much. I'd be delighted to answer questions, as would my colleagues.